And in this overview, talk, I shall try to discuss the practical impact that information theory may have, and that's beyond the classical role as a mathematical theory of communication. And emphasis will be put on wireless systems. Or do I change slides? Oh. Okay. So we'll start focusing on information theoretic insights, and it'll be really, really very, very short, and some overview on some basic information theoretic aspects and practical implications, emphasizing, as I said, modern wireless communication, mentioning references, only some recent studies in form of overviews, that's all, not too many references alone, and conclude with an outlook and maybe some interdisciplinary view. As we all know, information theory was born with this monumental paper of Shannon. And today, what I try to say, it's not only a theoretical, beautiful theoretical subject, but it has serious practical implications. In the not so remote past, the central problem was how to do. How do I implement this FM transmitter? What to do was clear. How do I implement this FM transmitter so a soldier can carry it on his back in World War II? That was the issue. What to implement was, what to do was clear. Now it's the other way around. What to do is the question. How to do, much less important. So you are very talented, you do it with 100,000 transistors less. No big deal. And information theory is exactly the answer to that. And that is why it has a truly practical role now. It addresses directly the problem of what to do, and more than that, what is ultimately best to do. And whatever I'll try to say is what Tara actually asked, that today, unlike Shannon times, where information theory was decades in advance of practice, now it's the other way around. The practical model, or the practical model that emerge, are not yet treated satisfactorily from an information theoretic point of view. We were not able yet to provide the right answers. It's just the opposite. Just to say that this is the classical model that Shannon came up with in his paper, maybe also I'm combining here a later paper of his in the 50s, of a Gaussian channel, classical Gaussian channel with Gaussian noise, a filtered Gaussian channel. And the question is, what is the rate that is ultimately possible to transmit over this channel with error probability of P? And that was Shannon's answer. This is the 48 paper, here it's the 59 paper, but the combination of two is the answer, the ultimate answer. And of course, if we like reliable communication where P goes to 0, that's the classical Shannon formula. If we have free bandwidth, this is the minimum energy per bit. We have to invest to get reliable communication. But the issue now, as Tara has mentioned, is not to try to improve over this using turbo codes. Turbo codes gets some LDPC codes 0.041 dB less than capacity. It's no more this. The models of modern communication is not do not break down to classical point-to-point communication. Just to look at some interdisciplinary aspects of information theory. Of course, communication and networking that we know. Shannon taught us. But there is a whole spectrum of EECS-related issues like signal processing, control theory, networks, computer technology, learning, complexity, analysis, storage devices, cryptography, from different aspects, physical layer cryptography, not only classical cryptography, and even circuit design that information theory has a role, without detailing too much. Connection to statistics and probability, that was classical. Even at those old times, some statisticians said, okay, the whole information theory is a sub-branch of statistics. That is classical. But now we have strong links to mathematics, just to mention graph theory, deterministic and random matrices. Actually, in our practical work, for practical model, we need results in random matrix theory that the mathematicians haven't yet provided us with. So we have to develop some of them. Physics, statistical physics, links like that. Yesterday, maybe I mentioned even one result in that. Quantum information theory, economy, investment policies, gambling, which is not exactly, maybe it is economy, and the like, biology, but a word of caution is in place. Fashionable misuse, buzzwords of information theoretic terms is very dangerous. Shannon again noticed that when? In 56 already. This is the paper he wrote, one-page paper, the bandwagon. Some examples where information theory played role. 2G technology. CDMA, we had here yesterday Doctors Jacobs and Viterbi, the entrepreneurs here. They use information theoretic concepts if you'll go back and look at the starting papers. Twisted pair technology, ADSL, VDSL, OFDM mentioned here, wherever, LTE, but wherever, internet, what is known as fountain codes, raptor codes, rateless codes, come from information theoretic ingredients. Wireless high-definition multimedia interface, HDMI. Tara mentioned, she gets television through radio, through the air, through the radio, and because it's digital, it doesn't have a graceful degradation like analog TV used to have. Is it a must? No. No. Multi-resolution and broadcast coding, broadcast multi-layer coding, solves that exactly. It should behave digital, but behave like analog. And this is the standard. And the same goes for digital audio broadcasting. Ad hoc networking, vehicle to vehicle, without mentioning too much details. MIMO wireless technology, that we'll speak about. How about C2 power? Energy saving via cognition cooperation, a European project. So relies on information theoretic concepts. If we go to MIMO if you wish, the information theoretic potential of coding a detection strategy started not so long ago, but yet really just looking at the number of papers that appear on this issue, and actually the applications, some of which we heard in the previous talk and the talk on the Beyond 4G. It's Very important technology. Just as I said, I will mention only tutorial overview papers. Appears an overview, though it's quite old now, with that technology, and addresses many aspects, like inaccurate child state information, which leads to mismatch decoding, an open information theoretic problem for decades. Information theoretic implications of training data. How do I acquire channels? Not trivial. And what's done not in LTE, not in LTE advanced, not in fifth generation is even close to optimal. Iterative, not only iterative decoding, turbo codes. The whole process should be iterative and unified without knowing what is the code, what is the channel estimation. What treats the data links of queuing should be one. And we see some efforts towards this direction in Huawei, a Chinese company. As we said, random matrix theory, a mathematical tool which plays key role in MIMO systems to really analyze theoretically the problems. Statistical physics, very linked to MIMO technology. Just the tools. Again, a tutorial FNT Foundation on trends monograph appeared recently. Cellular communication, we heard some. And actually, there is much more to do. I truly don't agree that the advantages or advances that we can have are marginal. Another quarter of dB by having a better code, another 3/4 of dB by having a better multiplexing system, not at all. First, many aspects appear, as said in recent tutorials. One is just to be out at the end of the month. And there are many things that are far from yet being implemented, like MIMO broadcasting for real. As far as coding aspects go, again, it's not that we try to break, I should correct myself, it's not that we should try to break a multi-user, multi-channel communication system into point-to-point ingredients and to then try to use efficient codes that come close to the Shannon Gaussian single point-to-point Gaussian channel. No. This should be implemented or thought of inherently combined with those MIMO systems over truly fading channel, considering spectral efficient communication. Either we work coherent, non-coherent, or in the mid-regime, examining coding based on that, but what's known dirty paper coding, which is more sophisticated, or binning in general, treating the inaccuracies in our channel knowledge, just compound channels, noisy phase channels, sometimes the noise is in the phase, like in optical communication. Wideband regime, source and channel coding. For now, at best, it's separated. Even worse, nobody does source coding today. Efficient communication in the presence of feedback. We do have feedback. Do we use it? Not really, just to estimate the channel at best. Cognitive radio that people mentioned here. Again, a tutorial, FNT, and now we saw the role, we saw a little on one slide, the role that information theory can play in practice, even on practical exit, extrinsic information transfer chart yesterday. No details here. How about polar coding, new thing? We thought it's a beautiful theoretical framework, but application, who knows? Alex Bardi here showed us that Alex Bardi and people working with him showed us that it might be different. Yes, it might be practical. With Adi Total, might be practical and actually compete with this. Who knows? And that's without even mentioning structured codes, like lattice codes, that will play a huge role because those seem to be matched to multiple access networks. It's not that we know by Shannon random coding achieves capacity. And now let's try to approach that, which was very, very clever because years, decades, till the 90s, we thought, oh, we should have this structure of minimum distance, so on and so forth, fair. Only then, let's try and use Shannon's intuition for real to make the codes look random. And the toolboy here was born. Then LDPC, which is not a new idea, the PhD thesis of Bob Gallagher. Structuring is very important, not just to try to come close to what random coding is, which is not implementable. Actually, in multi-access system, it's not that clear that structuring is not a math. It can beat random coding approaches. Forget the complexity of implementation. Don't even mention it here. How about multi-user detection? That we have already, at least at the beginning, we didn't have. Then 2.5 generation, 3 generation started to appear. Various different models to try and to idealize cellular systems so one can analyze them, appear inter-cell cooperation, inter-user cooperation. Questions that have been asked here, how do I do inter-cell cooperation with limited capacity backholes? Well, backholes could be very fat, but still, each cell in future generations has to deal with so much data that even those optical, let alone wireless, backhaul are finite. Cannot be considered infinite backhaul, infinite rate reliable backhauls. Linear and non-linear processing like pre-coding, we mentioned dirty paper, maybe I'll mention soon just to whoever is not acquainted, just to get some notion what it is. Large systems, spectral efficiency said that random matrix theory and physics, statistical physics are essential here. How about what actually Tara mentioned? Queuing and information theory. The combination is not that clear. Cooperative networks, as we said, relaying, collocated user transmit-receive cooperation, distributed transmission-reception. There are many, many problems that we don't know the optimal solution. Theoretical, I mean. Efficient coding approaches to networks, if not point-to-point that we have already. Actually, to networks, we combine routing and coding, and classical coding. Who said that we should route messages? What is this? That is the thinking of the 60s, maybe. And that's what we do, even in fifth generation things as we have. Who said that this is what we should do? Actually, all indications are that this is what we should not do. Network coding. but not the idealized network coding idea, you know, the classical. Noisy, what's called noisy network coding and beyond, which can be seen, again, that network coding is nothing new. It's just, you know, falls naturally within information theoretic concepts. Just if you take the right view. How about interference mitigation? Once, you know, at the beginning, people thought, including those specialists, Qualcomm at its beginning, that it's not doable. And then they self-do it, interference cancellation. Is this the way to go? Of course not. We have concepts of alignment in networks, that all interferences are so aligned to take a subspace, which says that the actual operation is not working within OFDMA or other orthogonal methods. Very different to cope with it with intercell interference. Quite modern approaches. Though, not everything that is theoretically or mathematically developed should be adopted. In practice, we should adopt only robust procedures. And that demands a special theoretical treatment at its infancy at best. Feedback we already said. Just a few words about writing a dirty paper, familiar to most of people. Just the question is how to eliminate interference at the transmitter. And for example, if we go to the Gaussian example, where the transmitter knows the interference. Why? It's not really an interference, it's just a transmission to another user. How does this get eliminated? You say, okay, just subtract it from the signal that you use to the user. Yes, but what if its power is much higher than you have? The interesting thing that you can do it at no cost at all, at no power cost, and get back the capacity like the interference was not there. Quite surprising, I must say, from the first glance. If we continue with system aspects, as we said, side information plays a huge role, almost not used so far at all. So joint source channel coding, not used at all. When separation is optimal, usually it's not in networks, and it is in point-to-point communication. When simple approaches are optimal or close to optimal, or you don't lose too much. We don't know too much about that. Hierarchical communication or universal algorithms, which is good. We do not want to adapt our algorithm to what we have. We want some kind of universal thing like universal compression. This Lempel-Ziv algorithm, which is applied in many places, including maybe the SPC even. As far as compression, the example, let us skip it, classical example, and other aspects. As we said, capacity is fine, but after all, we have delay constraints, must consider finite block codes, must know a bit more than capacity or ultimate information theoretic limits. And information theory answers also that. Actually, from almost its birth, addressing error exponents and the like, and other works, more modern works. Security, Physical layer security, not key-based algorithms. We know that, and somehow it's associated. Look, if I want to achieve physical layer security, the loss is so great in rates, forget about it. Not true? If you're not true in the classical Gaussian architecture. Why? True. You can actually have that rate that you transmit that is secure is low, but you can transmit as you did. Other rates which are not secure, having the full capacity of the direct channel. Connection to signal processing. I will mention just something that discussed yesterday with the implications on coding on the interference channel is the relation between mutual information, classical information theoretic notion, and MMSE, which is classical signal processing term, the mean square error of the optimal conditional mean estimator. Again, a tutorial, foundation and trend, will be published hopefully sometimes this year. As far as open problems, there are many. It's not that I'm going to count them all. And the issue is that the many must impact the way efficient communication should be approached. Again, not the old way, not trying to adopt strategies that turn the whole communication business to point-to-point communication. Not. Starting from the broadcast MIMO channel, which is very, very important on the downlink. As we said, MIMO with common rate, unsolved yet. Many users, 2 users solved, also not just recently reported by Nair in ITA a couple of months ago. Broadcast fading channel, we don't really know theoretically what to do or what is optimal to do. Interference alignment that I have mentioned will impact cellular communication, and indeed Huawei has quite a large number of talented people looking into that. Cognitive multi-terminal systems, network information theory, and its implications is just at its infancy. Marriage between network and information theory, as we said, queuing of information theory at its infancy. Impact of feedback, especially in multi-user systems, we don't know that much. Like point-to-point, we know exactly about noiseless feedback. Even that we don't know if the feedback link is noisy. Optimal distortion, which chance state information has many impacts, like how good are systematic coding approaches, just to mention some. And new insights by using new tools borrowed from statistical physics. And to conclude, my view is that advanced theory will impact the very notion of modern communication. It will not look like the systems we know now, with another advantage, with another improvement here and there. Not at all. Very different. Fundamental impact of what I mentioned, the combined network physical layers, cross-layer design, network approaches, cognition, network coding, or more noisy network coding. MIMO, we just started. How about massive MIMO, the ideas that we see emerge, going towards really green communication? Coding, we have discussed, it's not only turbo and LDPC point-to-point that we have. Much more than that. Universal algorithms. So whatever we seemingly looks like a mature field, information theory, it is not at all mature for those multiple user, multiple connection systems with constraints like delay, not at all mature. Most of the revolutionary theoretical view is at its infancy and yet hopefully to come. And interdisciplinary aspects I already mentioned with much cross-fertilization, like statistical physical information theory. The impact is all over. So with that, let me conclude.
Any quick questions for Shlomo? I think people are hungry, so. Okay, thank you so much. So, okay, so before we break for lunch, I want to thank the speaker again, and I wanted also to share with you what I've learned from this morning session. It actually goes back to before I came to San Diego. I used to work at Bell Labs and lived in New York, and we had a friend who was an avid artist and painter, and he studied art history, got a master's degree, and like all aspiring artists actually end up being a guide at a museum. And he was showing people the beautiful masterpieces that they had. And one day we asked him, okay, so what's the most frequent question people ask you? And he didn't take him much, and he says, oh, by far the most frequent question people ask me is, where are the restrooms? So I've been listening here to all these great talks, both from the UCSD folks and from the industry and from Shlomo, and thank you all for sharing your vast knowledge with us, and I've learned a lot. But the most important piece of information that I had is actually this, where's the keyboard? So, all right, so it's now 12:30. Let's resume at 1:15. We'll be 15 minutes late. Okay, thanks. Thank you very much. Thanks.